In this video, we use the periodic table to help us predict the electronic charge on some common ions. We will start by reminding ourselves that the formation of ions, known as ionization from neutral atoms, can occur in two ways. Loss of electrons to produce positively charged ions called cations, and gain of electrons to produce negatively charged ions called anions. Loss of electrons is known as oxidation, and it is metals that tend to lose electrons to form cations, with a common example being the formation of the Na+ ion from a neutral sodium atom via the loss of a single electron. The gain of electrons is known as reduction, and it is nonmetals that tend to gain electrons to form anions, with a common example being the formation of the Cl- ion from a neutral chlorine atom via the gain of a single electron. It turns out that atoms gain or lose electrons in very well defined ways. For example, a sodium atom tends to lose only one electron in an ionization process to form the Na+ ion. Magnesium atoms, on the other hand, will be transformed to the Mg2+ ion by losing two electrons. Aluminium ions tend to lose 3 electrons in chemical reactions to form the Al3+ ion. Now, it's no coincidence that these three elements appear consecutively on the periodic table at numbers 11, 12, and 13. It's also no coincidence that they exist in group 1A, 2A, and 3A if we use the old naming of groups, with the 1A sodium metal losing 1 electron, the 2A magnesium metal losing 2 electrons, and the 3A aluminium metal losing 3 electrons. The three elements also come immediately after the noble gas neon at number 10. So when sodium loses 1 electron, it ends up with 10 electrons. When magnesium loses 2 electrons, it also ends up with 10 electrons. And when aluminium loses 3 electrons, it also ends up with 10 electrons. They all end up with the same number of electrons as the noble gas neon. If we look at predicting ionic charges for nonmetals over the other side of the periodic table, fluorine will always gain 1 electron to become the F- ion. Oxygen will always gain 2 electrons to become the O2- ion, and nitrogen will always gain 3 electrons to become the N3- ion. Again, it's no coincidence that nitrogen, oxygen, and fluorine are all consecutive elements in the periodic table at numbers 7, 8, and 9. But this time they precede neon in the periodic table. So a neutral fluorine atom starts with 9 electrons in its electron cloud, and when it gains 1 electron, it ends up with 10 electrons. Neutral oxygen starts with 8 electrons in its electron cloud, and when it gains 2 electrons, it ends up with 10 electrons as well. And neutral nitrogen atoms, which start with 7 electrons, they gain 3 electrons to also end up with 10 electrons, the same number of electrons as neon. In fact, all of the ions formed from all of these atoms here all have 10 electrons, and these ions are said to be isoelectronic. Iso meaning the same, so the same number of electrons. And they happen to have the same number of electrons as the noble gas neon. So why is that relevant and important? Because it turns out that electron clouds of noble gases, including neon, are very stable, whereas the electron clouds of other elements are somewhat less stable. And what appears to be happening here is that atoms tend to gain or lose electrons to look like a noble gas. Atoms want to be stable. The electron clouds of noble gases are stable. And so if atoms can gain or lose a certain number of electrons to look like a noble gas, then they will attain stability. So it turns out that a metal tends to lose enough electrons to attain the same number and arrangement of electrons as the noble gas immediately preceding it on the periodic table. So sodium, with an atomic number of 11, has 11 electrons, will lose just 1 electron to end up with 10 electrons to achieve the stable electron arrangement of neon, the noble gas immediately preceding it in the periodic table. Nonmetals, on the other hand, tend to gain enough electrons to attain the same number and arrangement of electrons as the noble gas immediately after it on the periodic table. So fluorine, with an atomic number of 9, has 9 electrons, and it will gain 1 electron to end up with 10 electrons to achieve the stable electron arrangement of neon, the noble gas immediately after it in the periodic table. And so this means that the periodic table, and more importantly the position of elements in the periodic table, can actually be used to determine and predict ionic charges. For example, all of these group 1 metals will lose 1 electron to look like the noble gas immediately preceding it in the periodic table. So lithium at number 3 has 3 electrons in the neutral atom, which is not a stable number or arrangement of electrons. If it loses 1 electron to become the Li+ ion, it takes on an electron cloud arrangement that looks a bit like the noble gas helium, which is number 2 on the periodic table. What do we know about helium? Helium is very stable, which is why lithium tends to only lose 1 and only 1 electron. The same applies for the rest of group 1, or the group 1a metals. Sodium loses 1 electron to become the Na+ ion and takes on a stable electron cloud arrangement that looks a bit like neon. Potassium will also lose 1 electron to become the K+ ion and take on an electron cloud that looks like argon, and so on down the group. Similarly, group 2 or group 2a metals will lose 2 electrons. Magnesium at number 12 will lose 2 electrons to look like neon. Calcium at number 20 will lose 2 electrons to look like argon. And strontium at number 38 will lose 2 electrons to have the same number and similar electron cloud structure as krypton, number 36 on the periodic table. What do we know about neon, argon and krypton? They all have very stable electron clouds. If we pop over to the other side of the periodic table, we can see the examples aluminium and gallium in group 13 or group 3a. They will lose 3 electrons to gain electron cloud structures similar to neon and argon. So the old naming convention for groups 1a, 2a and 3a is useful here, since elements in these groups will lose 1, 2 and 3 electrons respectively. For metals in the middle part of the periodic table, the so-called transition metals, predicting the charge on cations from their position in the periodic table is a little more tricky, and the charge on only these 3 elements here, zinc, cadmium and silver, can be easily predicted from their positions in the periodic table, with zinc and cadmium in group 2b forming 2+ ions and silver in group 1b forming the 1+ ion. We'll see in just a moment that the rest of the elements in the middle part of the periodic table can actually form multiple ions with different charges, so predicting charges of metal ions derived from elements in the middle part of the periodic table becomes more difficult. If we go to the nonmetals, we can see the halogens here in group 17 or 7a, that's fluorine, chlorine, bromine, iodine, all gain 1 electron to attain a 1- charge. Fluorine at number 9 gains an electron to look like neon at number 10. Chlorine at number 17 gains 1 electron to look like argon at number 18, and so on down the group. The halogen group lies 1 group left of the noble gases, and they form a 1- charge. The chalcogens in group 16 or 6a lie 2 groups to the left of the noble gases and form ions with a 2- charge. So oxygen at number 8 gains 2 electrons to form the O2- ion to look like neon at number 10. Sulfur at number 16 gains 2 electrons to become the S2- ion to look like argon at number 18, and so on down the group. And finally, nitrogen in group 15 or 5a sits in a group that is 3 groups to the left of the noble gases, and it forms a 3- ion. Starting with 7 electrons in the neutral atom, nitrogen will gain 3 electrons when it forms an ion to look like neon, the noble gas, immediately after it in the periodic table. So we can predict the charge on many ions from their position in the periodic table, but it is largely limited to just the main group elements, that is, elements in the S block on the left-hand side of the periodic table or the P block on the right-hand side of the periodic table. And you can see some examples of the ions formed from main group elements in this table here, including the 1+, 2+, and 3+ cations formed from groups 1a, 2a, and 3a metals, and the 1-, 2-, and 3- anions formed from the nonmetals lying 1 group, 2 groups, and 3 groups to the left of the noble gases. As I said, it becomes a bit harder in the middle part of the periodic table with the transition metals because we can't necessarily use their position in the periodic table to predict the charge on the ion, and many of them have more than one charge that gets formed. For example, we can see here that copper forms both the copper 1 ion, Cu+, and the copper 2 ion, Cu2+, meaning that copper can lose 1 electron or lose 2 electrons depending on the circumstances of the chemical reaction. Similarly, cobalt can lose 2 electrons to become the CO2+ ion, named as cobalt-2, or it can lose 3 electrons to become the CO3+ ion, named as cobalt-3. Similarly, iron 2 and iron 3 cations can be formed from the loss of either 2 or 3 electrons, depending on the chemical reaction conditions. Finally, the other thing we need to consider is that ions are not just simple monatomic ions resulting from the loss or gain of electrons from elements in the periodic table. They can also form from chemically bonded groups of elements that gain or lose electrons, which means that ions can also be polyatomic. And here are just a few examples of the most important polyatomic ions we need to remember, including the hydroxide ion, the nitrate ion, the sulfate ion a little further down, the carbonate ion, the phosphate ion, and the most important of the polyatomic cations, the ammonium ion. And remember, the reason we need to either remember the charge on ions or predict the charge on ions is so we can readily predict or determine the chemical formulas of ionic compounds made up from cations and anions of known charge. And that is the subject of the next video in this series.